In Lab 3, the objective is to find the mass of a black hole given the mass of a star orbiting the black hole, the position data of the star in the black hole, and the time span. In order to find the mass, we'll utilize the program VPython and the fundamental principles of Newton's second law as well as the momentum principle. As a result, the mass of the black hole was calculated, however, the estimation was flawed. Given thorough and correct procedure, it cannot be determined where the mistake lies, but the application of the fundamental principles are understood. The initial conditions are as shown. The position of the black hole is 3.00 times 10 to the 10th, negative 2.00 times 10 to the 10th, 0 meters. The mass of the orbiting star is 1.989 times 10 to the 30 kilograms. All the position data of the orbiting star can be obtained in stardata.csv, which will be used for our program. The final position of the orbiting star is 2.31 times 10 to the 11th, negative 1.44 times 10 to the 12th, 0 meters, and the time span is 86,400 seconds, which is also 1 day. Here we can find our initial conditions. The mass of the star shown here, delta T is 86,400 seconds divided by the number of entries for the position data, so that way we have the change in time between each position, and the first observation data point is at a time of 0. In order to find the mass, we have an objective to first calculate the net force. To find the net force, we will utilize Newton's second law and the momentum principle. In this context, dp dt perpendicular plus dp dt parallel equals dp dt, or F net. To be able to calculate the net force, we will have to use calculus to determine other quantities like velocity, momentum, and the change in momentum. Given that stardata.csv contains all the position data of the star, the change in position is calculated in a while loop by using the index minus the preceding index. From here, the change in x and the change in y are found. Using another while loop, the final and initial velocities are calculated using the change in x and the change in y. Then the initial and final momentum is calculated using the change in velocity with a small enough time step. dp dt is defined as the change in momentum over the change in time. The momentum principle is displayed as F net equals dp dt, and the formula is manipulated to obtain other values such as the parallel and perpendicular components. Knowing these components will allow us to visualize the direction of these components while we watch the program run, as the star will project arrows. The momentum principle is displayed as F net equals dp dt, and the formula is manipulated to obtain other values such as the parallel and the perpendicular components. Knowing these components will allow us to visualize the direction of these components while we watch the program run, as the star will project arrows. When we run our program, we can see that the black arrow represents dp dt parallel, the blue represents dp dt perpendicular, and the yellow represents the net force. dp dt perpendicular is always pointing towards the black hole, and F net changes as the star orbits. After a while, dp dt parallel changes direction opposite to motion, so the object is now slowing down. At the moment dp dt parallel changes direction, dp dt perpendicular and the net force are equal because the velocity becomes constant. If we take a look at our module, we can find that the net force calculated at the bottom, right here, due to the print statement in the code. The net force is 3.5572 times 10 to the 33rd newtons. When we calculate the mass of the black hole, we have F net to be 3.5572 times 10 to the 33 newtons. And we use the gravitational force formula, which is F net equals gravitational constant times the mass of the black hole and the mass of the star over the distance squared. The distance would be the final position of the star minus the position of the black hole, which was given. And if we calculate that, we find the mass of the black hole to be 5.4899 times 10 to the 37 kilograms. When considering what if and what does it mean, Fnet and dPdt are two separate concepts. Though experimentally Fnet always equals dPdt, it must be understood that Fnet is the force that causes the change in momentum. Fnet can exist without dPdt, but dPdt cannot exist without Fnet. Given that explanation, in a scenario where the known mass of a black hole was replaced with the black hole with an unknown mass, and if the motion of the star remained unchanged, then it would not be possible to find a different mass. If the motion remained the same, then the causation, or the force, also remained the same, and with the other constant variables, it is only possible for the mass of the black hole to remain the same too. All in all, we observed the motion of the star orbiting a black hole to determine the mass of a black hole. Though we were not successful in finding the correct mass, the momentum principle was understood and analyzed in this context.